Great.
It's not nice out.
Do you guys have your Quackmolus?
You're going there.
Quackmolus?
Quackmolus.
I guess. If she doesn't show up, I'm going to be very angry with her.
Jesse, where's Jesse?
Good question.
So guys, since you track people are leaving soon, let's quickly look at some of these word problems. Let's just discuss them broadly for a second. Just like look at them and go, it's all review, none of it's new. And can you take your AirPod off, please?
It helps me interrupt you less.
Oh my goodness.
Okay?
Please, just
It helps me interrupt you
help
less.
me.
Just trust me on this.
You guys. It's like chewing with your mouth open.
Oh no.
Well, you can't even see my mouth because it's behind my mask.
Okay. So 10 is it should be part of my job. It should be part of my job. So average value.
Where are we?
Well, number 10 is the first word problem, right?
Thank you. Sometimes we skip.
How do you calculate average value? Keeping in mind, this whole problem set's all about integrals, right? So that should be,
Take the integral.
it's the integral of the function divided by
The sum.
The area.
the span of whatever interval you care about. So in this case, x plus cosine of x, that's a wiggly function,
Wiggly, wiggly.
right? Because cosine looks like this, at least from 0 to 2 pi, it looks like this. It completes one cycle. And x looks like this. So if you add them up, you get something like, something like that, like something wiggly. It's a curve added onto a line. Maybe it gets lower than that, I don't know. But anyway, so then the average value would be the integral of your function, which we know how to do that now. And then you divide by the width of the interval. Okay? So we do that dividing by 2 pi at the end. 11's the same thing, average value. 12. Same thing.
Okay.
Average value, right? 13 is about just what's the area bounded between two curves. So something that makes this one a little bit more challenging than than just what's the area under this one curve is there's two curves to look at. So there's kind of a hint. Which one do you think maybe we should graph first to situate our brains in the right place?
X squared.
I'm thinking the parabola.
X.
Because that'll give us a hint as to where the other graph kind of lives, maybe.
Maybe.
Because they got to cross at two reasonable points, otherwise the problem's like not doable. So how do I graph this? We know, it's a parabola. If you're a little unclear, it's a parabola. That tells me it's a parabola. And if you factor it out now, you can see there's two zeros at 0 and 1. And so the parabola is going to look something like this. And I have a strong feeling that the sine function is going to cross it at those 2 points, right? Does that actually come true? Well, let's see. When does that guy? We know that the sine of 0 is 0. And what's the other theta value? Sine of pi is 0. The sine of 1 is like.
We were multiplying it by 1.
Hold on, what?
And
Yes, x is, yes, if x, so this is true, these are two basic math facts. If x is 1, yes, that's everything, that's correct. If x is 1, then this reads sine of pi, which is 0. So that tells us that this curve completes one oscillation, or sorry, it's actually half a cycle. The whole graph would go pew and then keep going, right?
Yeah.
Keep going forever. But this is the region that we really care about. And so how do you find the area of a region like that? Yeah, you're going to subtract them. So it's going to be the integral. What are the bounds of my integral?
0 to
1. It's going to be the top function, sine of pi x. That'll involve a really simple reverse chain rule to integrate. And you're subtracting. You're subtracting the parabola.
So I get why the sine is doing that. Why is the parabola crossing at pi?
It's crossing at 1.
Oh, I get it. Okay.
If there was no pi here, the graph of sine of x crosses at 0 and pi, but when you put that multiplier in there, it crunches it up a little bit. So now when x is 0 or 1, you get, and the next 0 would be at 2 and 3. 14 is, hey, look at this velocity function. Can you tell us the position function? How do you get the position function out of a velocity function?
derivative.
It's the integral. Antiderivative, right? It goes,
Yeah.
it goes position, the derivative of position gives you velocity. The derivative of velocity gives you acceleration. So the reverse, the antiderivative of acceleration gives you velocity, the antiderivative of velocity gives you position. And then how do you use that t equals 0 info? What the t, so when t is 0, the position is 10, that's going to tell you about the c value. 15 is about total distance. Same kind of story. The difference, though, is so this marker sucks. Who thinks they know why finding distance on a sine function is a little? Oh, I think I went to the recycling bin. Sorry. Sorry, conservation team. I'll get it later.
What'd you say? Oh, yeah.
No, I'll transfer it.
That's straw.
They should make them refillable.
If you mentioned for the right way.
Huh?
You quill the right
Will.
A marker quill?
Yeah. Just go dry erase.
Like that would take a lot of effort.
So between 0 and 5, when is so sine of pi t? Where does that guy hit the x-axis? 0.
0.
Well, let's see. 0. Why does it hit the x-axis at 1? Because the sine of 1 pi is 0. And why does it hit at 2? Because the sine of 2 pi is 0. 3, the sine of 3 pi is 0. The sine of 4 pi is 0. And the sine of 5 pi is 0. So why is calculating distance here a little bit more complicated than calculating displacement?
Because it's negative.
Because there's say between time 1 and time 2, that's negative velocity. So what direction is the particle moving?
That way.
Left, assuming you're using right means positive, left means negative, which we typically do. So for the distance, what you're going to do, I mean, you could talk about this. It's a good way to get Mr. Computer to help you check your answer.
Would t be equal to the diameter of the circle?
No. Wait, what circle?
So like the sine function does like the triangles, but it's also like mapping the circle. That's why the movement is going up and down.
So, yeah, so if you're mapping, so the question is talking about really a particle, here's the origin and it's moving left and right. It's actually oscillating between 1 and -1. And it's doing basically in this, but over the 5 seconds it goes, right? It goes forward, backward, forward, backward, forward, back to the origin. Now, if you want to connect, you can do you can connect that to, as you travel around a circle, right? Look what the sine values do. They go from 0 to 1, back to 0 to -1 to 0. What this pi does is actually changes the rate at which you travel around the circle. So say you're using time. When time is 1, you've gotten from here to here. So time 1 corresponds to living there. And then time 2, time 3, time 4, time 5. That make sense?
Mhm.
So anyway, here's a computer can do that all at once. When you do it by hand, you have to say, well, I don't really have a fancy technique for doing the absolute value of a sine function. So what will I do? Anyone know the answer to this?
0 and 1.
Exactly. I'll go from 0 to 1 and then just multiply that number by 5. Right? So I'm going to find that area. So this area here is the integral from 0 to 1 of sine of pi t. And then that will tell me how much distance was covered between time 0 and time 1. And then I know, well, same distance here, same distance here, same distance here, same distance here. Makes sense?
Mm-hmm.
Oh, by the way, Rafe, if you want to talk about the radius of the circle, it would be like if you had a constant here. So if you put like a 7 here, that would kind of, in a sense, be like making the circle have a radius of
Yeah,
7.
so if it's always multiplied by 1, because if that's the case, you can pretty much just count it, can't you? Because that equals 2, doesn't it? It's might get rid of the 7.
Get rid of the 7.
Yeah, that's 2, right?
Oh, and say basically I know he's going from 0 to 1.
Yeah.
Yeah, that argument makes sense. Yeah, for total distance.
Yeah.
I'm trying to make sure. Because the pi, you're going to end up with, you have to put a pi here, and then a 1 over pi out here. And so your integral ends up being, like I'm having a, because where does the 1, so the 1 over pi would go, so you'd have 1 over pi negative cosine of pi t, from 0 to 1. And then, so you plug in the 1, so that would get you a 2 in here, right? Because you have 1 minus -1.
Oh.
That makes sense. Possibly. So, oh yeah, okay, I realized, sorry, Rafe, I realized I'm being stupid. Sorry, being tired. These 1s and -1s that's the maximum velocity and the minimum velocity, sorry, not the position. So I guess when you're talking about mapping this to a circle, you're really talking about these are velocity values, not position values. That makes it more complicated. It's like your answer ends up being 10 over pi.
Yeah.
Does that make sense?
Yeah.
Okay, so it's a good question. I had to think about that one for a while. I was like, wait a second, yeah. I confused myself because I for a second I thought this was, that picture is misleading. Sorry, you're not moving between 1 and -1. You have to calculate what's your maximum position here. Your max position would be actually not 2, right? Because between time 0 and time 1, we've shown you travel a distance of 2 over pi. And that means that, and between time 0 and time 1 was going from here back to the origin. So I think that means this has to be a pi. Do you guys agree?
Did you just say a pipe?
You guys agree with that?
Yeah.
Because then, yeah, you go there and back is 2 pi, and then left and back, that's left and back, and then right and back, and then left and back, and then right and back, making 10 pi. So
It's positive on the velocity graph, isn't it moving to the right?
Yeah.
the whole time? So wouldn't it be going between 0 and 2 pi? Or 2 over pi? That's what I was trying.
oh, for the position?
Yeah.
Yeah, it does make sense. Maybe you're right.
Then it's just returning to the origin.
Huh?
Since the negative and positive are the same, it's just always going to return to 0
Oh yeah, you're totally right.
after a full cycle.
Yeah, you hear what Dylan said? He's
Nope.
correct. Dylan said that this all corresponds to rightward movement, because his velocity is positive.
Oh.
So therefore, that distance he covers, which the integral tells us, but the integral's not gonna lie, right? So this area, 2 over pi, must correspond to the distance he covered while moving to the right. So I agree with Dylan. That should be 2 over pi. And so I think maybe my problem is my zigzag, too many zigzags, right? I should actually say, the full story is
Full story.
he, this is why it makes it confusing. Bye guys, have a good race. He's accelerating and then he's slowing down over that first second. So he speeds up and then slows down and hits this. So when he lives here, that corresponds to this moment in time. Then he turns around and goes the other way. So, okay. Sorry, we got more in depth there than we really kind of needed to. The principle here is you have a velocity time curve. You can take the area, like all I was trying to show you really ultimately was that the integral of the absolute value function from 0 to 5 is the same as the integral from 0 to 1, and then just multiply by 5 at the end. Yes?
Correct.
My question, how did you get 2 over pi? Because when I do the math, I get -1 over
Let me see. So, okay, it's fine. So you got the 1 over pi out here. And so you plug in 1. So negative cosine of pi. Cosine of pi is -1, right?
Mhm.
So this would be -1. And then you got to go minus negative cosine of 0. You got to plug the 0 in, right?
Mhm.
But cosine of 0 is 1, so it's minus -1. That's where I'm getting the 2 from.
I did it as like pi times 0 is like cosine.
Yeah, that one that's a tricky one. You got to know that, yeah, cosine of 0 is 1. Cosine of 0 is 1. Make sense?
Yes.
Okay, where were we? Let's move on. So, 16 similar. Same kind of question. 17 is all about, we've done these problems a bunch of times, right? Where you got like sand pouring into a container at some rate, where you got a rate function. How do you figure out how much sand goes into the container between, say, time 2 and time 14?
Measure from 0 to 1.
It's the integral
No.
of the rate function, right? So like a good way to remember that and just kind of make sense of it is to think about how, what does it mean when you say, take my rate function, and what is that dt doing, like when you integrate? Well, this would be, was it pounds per kilograms per minute?
Yeah.
So your rate is talking about kilograms per minute, and time would be minutes. So what happens when you do kilograms per minute times minutes? Well, that would tell you about the kilograms, right? That's called like a dimensional analysis. And then you say, well, okay, fine, that's telling me about the kilograms. If I go from 2 to 14, that would tell me the net amount that went in between time 2 and 14. So I would then just have to add that onto. So the amount that flowed into the container, right? What would I add that onto if I wanted to know how much is actually in the container? The initial amount. So what this in a picture might be like, here's the container, you know, I've got 180 kilograms to start. That's at time 2. And then between time 2 and time 14, I accumulate, you know, this amount, whatever that amount is, and that's the amount that I add on.
Mhm.
Good feelies there? Some Snapchats. Oh. Sometimes people be emailing the entire staff, and I'm like, that doesn't hit different.
I think it does hit different.
It does or doesn't? I can't remember. Hitting different's good, right?
I don't think that is a good thing.
Oh, okay, sorry. Then it doesn't.
Is it? I don't know.
What?
It's like
Like
that
Dino Nuggets.
McDonald's Sprite. It's different.
McDonald's Sprite? It's
McDonald's
different?
Sprite. It's different.
What's an
That
example?
is a fact.
Vis-a-vis
Vis-a-vis
regular
McDonald's
Sprite.
It's better than regular Sprite.
What defines
It's
regular
really different.
Sprite? Like store-bought
Yeah.
Sprite? But then could
McDonald's
you
Sprite
argue that-
It's different than
Different
regular
stores have
Sprite.
different
You guys
stuff.
can corroborate this?
Seriously.
Kelly Jo, you
Go
agree?
buy a bottle of Sprite, it's gonna be the same.
You agree?
Okay.
But if you get
McDonald's,
Sprite out of the McDonald's fountain machine, it's gonna hit different. Why are we arguing about this? The point was, when it hits different, it's good.
Okay.
Aspintoke, you agree with this? Okay, it's good. I feel like a little lost in the weeds here.
I'm
Sorry.
slowly picking it back up. It's all clicking now.
Off clicking.
It's all clicking.
Okay, so 18 is all about, that's a simple one really, just because at least the phrasing is simple. It's just what's the area between two curves? Well, you just got to draw the two curves. We just did an example a few minutes ago of what that looks like calculation-wise. 19's the same way. One thing that adds a little bit of difficulty to these is you have to figure out where they cross, right? So you're typically looking for like some simple X value that's going to make them be the same number. What's wrong, Abe? You okay over there?
No, I'm fine. Yeah.
20 is the same. And 21 says there's immense niftiness. Pretty
What?
good. Immense niftiness. I actually don't even remember why I wrote that,
Oh,
bro, honestly.
did you like look it up on the Desmos?
Let's look at it. I don't know. I can't remember.
I can't remember. Do it.
Let's get it.
Get it. Some-
Okay, consider this function. What kind of function is that? First of all, it's also, you see what number the question is, right?
It's a big number. It's a big number.
Something came in the mail today. 21. That's such a good Lamau. This is all a setup. No, it wasn't. Actually, it wasn't premeditated.
It wasn't.
No, I just realized that it was number
Shame.
21. God, I love memes. So fun. It just make me laugh.
Yep.
Okay. Good meme.
Good.
I saw a good meme today and I couldn't even relate to anyone on it, so it was kind of sad.
Not Miss Vestal? No.
No, she left me unread. I sent her the Snapchats.
Oh, that's
and
what
she
you're talking
she,
about.
She unreads them. She doesn't read them. I'm like, you left it. You didn't unread it. Good morning, Mr. Thompson. How are you today?
I'm good. How are you?
Not
How's it going?
too bad, I guess.
But I guess.
Okay, so this curve. So it says write a function that gives the area under the curve between 0 and some arbitrary number, some choice of n, and then include a sketch. So the sketch part's pretty easy, right? That's quick. Did you tell me you were a sovereign citizen?
Yeah.
And we're not subject to the rules and regulations of this institution?
Exactly.
Good, that's what you gotta do. Don't let them stop you. Okay. So it says write a function, area function.
Bless
So
you. I acknowledge your sneeze.
area function. So what would the area of this function between 0 and n be? How do you write that? Between 0 and n of the function. Are we okay with that?
Yes.
Now, in the old days, we might have had to be like,
In the
Oh,
olden days.
in the olden days, yeah, that's about as good as we can do. But now I'm like, actually know how to integrate that function. That's nice. What's the integral of e to the negative x?
Negative 1 times.
Yep, negative 1 times e to the negative x.
Ah, I'm so smart.
And then you got to go, well, this is actually a definite integral that goes between 0 and n. Okay. Oh, I see the niftiness now.
And then?
I get it. Because watch, because now I can plug in the n. Remember, this is all a function of n.
Yes.
So plug in the n, you get negative e to the negative n minus, plug in 0.
No.
What's, yeah, you're going negative e to the 0, so this is negative 1.
Yeah.
And so let's write this a little bit more nicely. Minus negative 1 is positive 1. Okay, so this is my function.
Okay.
And then the question is, what happens as this function approaches infinity? It seems fancy. I mean, I didn't ask you to use limit notation, but we could do it just to flex.
Does it approach 0?
This purchase one.
1?
Yeah.
0.
The limit of our function, well, let's write it. Old-fashioned way is, old-fashioned way is back to early times. As n approaches infinity, so as this number, as your choice of right bound goes to infinity, your area approaches 1. That's kind of neat. Isn't that neato burrito? Just one. Just one.
Burrito.
That's how much area is trapped under the.
1?
Well, it's crazy because you might think back to the there's various. It's not a true paradox, but
Oh,
think of that shape.
Gabriel's horn.
It's related to that exactly. This shape has infinite length. Right? Imagine that little
Oh wait,
slice.
so if you rotated that around the x-axis, it would have a volume
The
of
black
pi.
hole.
Well, okay, we're gonna get to that. Let's do it. We'll do it today. We have time. Because that one wouldn't be that. Well, you could rotate this, but then it wouldn't be that shocking because you'd say, well, you just showed me that there's finite area under that, right? Does that make sense? This area never goes above 1, and as you approach infinity, the area approaches 1. So then, okay, if I could show the integral, but you could wrap that around the x-axis, and then you'd have a volume that was also finite.
But the surface area.
This would have that's a little bit more complicated one. I put it in here. It's what's the next one?
Oh, my bad.
Yeah, what
Thank you.
In honor of Taylor Swift.
No.
You like T Swift?
No.
Philistine. Yeah.
Not as good as M-Train.
So what Gabriel's horn is, the paradox there is you have a shape with you have finite volume but infinite surface area. Calculating surface areas is more of a Calc 2 topic. Because well, in Calc 2 you cover like arc lengths. You'll learn how to calculate like how long is this curve. And then with that, you then talk about surface area. But anyway, so I wanted to talk about 22. So, but anyway, before we move on, does that make sense? This last question.
Yes.
So, area trapped under the exponential decay curve, even if you go to infinity, is still finite. It's only 1.
Well, if we have time today, can we also do 8A and B?
Yeah, brah. Of course. Don't let me forget.
Okay.
Come back to that.
Could you like apply exponential decay to like say the economy that it could never truly go underneath a certain point? Because you just said that it always has to be within that point, right?
Man, you can fit data, say economic data, to curves, but I don't think it ever would ever make sense to say.
Yeah.
Like, okay, a good example, the simpler example is, a car, you buy a car and you can model its value, roughly its depreciation as exponential decay. But I would not think it's a valid inference to go, well, therefore the value will never hit zero. Because, well, at a certain point, you have to pay someone to take the car off your property.
Yeah.
If it's that much of a piece of crap, like if the engine's just
If
totally
it's that
seized
bad.
and like there's nothing of value with it, it's just pure scrap metal, you're probably going to pay someone to come get it. So in that case, you have negative value. But, does that make sense?
Yeah.
But certainly, at certain times, you can model economic growth and decay using exponential curves, but especially long term, S&P 500 growth over a 50-year period, you could say is approximately.
It's more complicated than that though, because it's not necessarily that they're paying for the thing, it's paying the labor overdoes the actual cost of the
With the
material.
car example?
Yeah.
Right. I just mean, when I say value, I mean for you personally, how much could you sell it for?
Okay.
You buy the car for $10,000. Next year it's worth $9,000. Next year it's not worth $8,000. It's worth like $8,200 or something. And then, of course, it's not a perfect curve.
Yeah.
And
That's
Yeah.
kind of what I was thinking.
it's it could be jaggedy. There could be little dips in it, but
But you talked about it being a little
Well,
negative,
at some
and
point,
so
it
it
does
can't be done by
increase.
And it's not necessarily the car's value itself is negative,
You
it's
can
the
appreciate
labor
old cars.
needed to move it becomes more negative than the actual value of the car. Because you could still theoretically sell that little piece of metal for something.
Have you ever been down to that like plane?
right, the value of something always includes the labor.
Plane?
Like,
You buy the car in the first place,
Old.
that price contained all the labor that was put into it.
I'll wait till I'm 70 years old and then I'll bring.
Anyway, it's good stuff. It's good stuff. Okay, so 22 says, consider this curve. This is a famous curve, 1 over x. And I'm only going to look at the right half of it. I'm going to ignore the other tail because the question says, write a function that describes the area under the curve between 1. So by the way, this is the point 1, 1, this particular curve. This is also this connects to a really, really fascinating result that I think it's really amazing, but never ceases to amaze me. So same idea. You guys can finish this one, right? Like this first step. What's going to be the function that you tell me an n value and then your function spits out the area between 1 and that number? So if you plug in 7, your function tells you the area between 1 and 7. What's going to be the answer to this one, guys? Anyone out there?
I haven't. I think it's, is it the natural log of n over n?
Yeah.
What was it?
I have natural log of n minus natural log of 1.
Yes.
But
So
then does that simplify the natural log of n over 1 or natural log of n over 1?
Good.
Okay.
yeah, there's 2 ways. So we all know that the antiderivative of 1 over x is log, right? Log of x. Say ln.
Line.
This?
To me, that looks like an abbreviation for the word line, so I just say line.
I just say log. 'Cause
Natural
If it's-
log.
you can say natural log or log natural, but unless you're talking about various bases simultaneously, then there's only one base we're dealing with for this question. So I can say
It's just personal, just
I
stupidness.
just feel like the feelings.
Easier to say. Sorry.
Rejoice. JB is in the house.
Oh, I was going to murder you if you
Okay,
didn't
I was
show
getting
up.
fully mad about it.
Now
Ugh,
that hits different when you think JB is absent, but she's not.
that does hit
Right,
different.
fellow Zoomies?
Don't worry, I made sure that I was gonna get back in time.
Yeah. How's it going, Jesse?
Jesse, did you get Moderna?
Pfizer. Yep, second
So-
shot in the arm.
The arm.
In the arm.
So like Trey said, you could lump this into one, you could call that log of n over 1, that's a log property, or also, what's the log of 1? Just, what is that number? 0. So look at that. So your area function is just the log of the number you picked. So so in the case of 7, like, oh, it's how much area is trapped under this curve between 1 and 7. That number is actually just the natural log of 7. That's kind of neato. Now, wait a second though. What happens to this as n gets really big? What happens to the area? We'll just say A. Well, what happens to this if n just grows and grows and grows?
But it just grows.
They approach it.
And we know that because, well, there's a whole bunch of arguments, but the simplest one is just, does this graph have a horizontal asymptote? Nope. We know there's no bound to it. It grows real slow. Like if you graph it, it's like this. I mean, it's not very fast growth, but it does grow really slow. It grows forever. And one last comment is, if you're like, if someone's skeptical of that, you say, does that ever hit 100? Does it ever get a y value of 100? And I'd say, yeah, of course it does.
A big number.
When n is e to the 100th power, right? Which is an enormous number, but it gets there eventually.
It gets there.
I mean, e to the 100th is absolutely astronomically large number. That's how big of an x value you need to have to get just
Oh my
100.
god.
What?
It's such a little function that could.
Yeah. So now this is there's even a health warning on here on Part B. Watch how nifty this is. This is beautiful. So this area as you go could be potentially infinite. Okay? There's no bound to how big this can get. However, if you rotate this around the x-axis, rotate it around the x-axis.
I'm not judging.
Remember how to do that?
Well,
Yes.
Circle.
Why?
Yeah, this is gonna, when you rotate this, revolve it, it's gonna create a whole bunch of circly worklies, little discs.
That's the thing.
Okay, a whole bunch of little discs, right? I tried to make it sort of not a very good drawing.
It's just pi times
Oh.
r1.
I thought it was very good.
So in any case, I'm gonna redraw the disc over here. Right. What's the radius of the disc?
1 over x.
The function's y value is the radius of the disc. How thick?
DX. This is bringing back that.
So the volume of that little disc is pi r squared. And then and then times dx.
Yeah, I was gonna say.
And then you integrate from 1 all the way to n.
Wow.
It's gonna be nifty, Jesse, I promise. It's gonna be real nifty.
That was the last problem.
Isn't it just
Well, the first thing that's crazy is, well, let's finish on that. I'll try to remember to come back.
First thing that's crazy.
Well, what you missed, Jesse, the previous problem, we showed that under the exponential growth curve, there's finite area. This curve looks pretty dang similar, but it's not. It's infinite area. That's kind of weird.
Weird. No, that is cool. I like it.
So let's see. The integral, pull the pi out.
Rip around.
And so the integral of 1 over x squared, that's what we've done a million times, right? Negative 1 over x.
Yes.
And you evaluate from 1 to n. And so you get pi times, so plug in the n, negative 1/n minus negative 1/1. And so weirdly, sorry, I'm trying to squeeze it in here. Your volume function, volume at a given n value, that's positive 1. It's pi times 1 minus an nth. You feels me? Make sense?
Yeah. Yeah.
But
Nah. Alas.
what happens as n gets really big? Look at that.
Zero?
Well, now look carefully. As n gets really large, that term becomes really small, but I still have 1 minus a teensy weensy.
So is it still one? Pi?
So the volume approaches pi.
Yes.
That is very nifty. Come on. If you don't like that, then that's just an
I hate
SMH in my
you.
head.
No, I'm just kidding. I don't like
Yeah, you weren't meant for this
That's a
world,
big
and I
move, no
already
cap.
knew that.
Can we go through those problems?
Yes, Aaron.
Yes, Aaron, I guess.
I'm gonna, don't worry, Jacob, I'm gonna go back and watch the video.
Fun fact, last
Dale.
thing. Don't worry, Aaron. I got you, bro. But this relates to one of the most amazing facts in discrete math, which is that if you go 1 whole plus 1/2 plus 1/3 plus 1/4, that and theoretically that approaches infinity, which is crazy because it should amaze you just because if you go 1/1 plus 1/2 plus 1/4 plus 1/8 geometrically, that would just approach 2. So how come he's just 2, not very big. He goes to a bazillion jillion. So that's weird.
That
Okay.
is weird. Wait, why is that? Okay, no, I'll.
Well, the answer to this, a good proof of that is actually just doing this calculus problem because you can show how you can relate this integral. This integral ultimately is talking about adding up like
The way to do it.
really to the Riemann sum basically. You can talk about how this area is lower than like a Riemann sum that you construct on it, and then show that the integral is infinite, so therefore the Riemann sum must be bigger than that, it's also infinite, and then you've proved.
Bigly, bigly.
There's other nifty proofs too, where you rearrange it. You do this really clever rearranging of the series and show that it just never stops growing.
Indubitably.
Which one, Aaron?
8A and B.
Okay, fellow king.
Hello, King.
8a is of the form u prime times u to the n. So let me ask you. Who's the u?
Sine squared times 3x.
No, it's just the sine of 3x is the u.
Oh, okay.
So cosine is the u prime. So 8a, so the way I'd rewrite 8a is it's cosine times, oh, sorry, it's a 3x, my bad. Cosine times the sine squared, sorry, negative 2 power, my bad. And so I go, oh, wait a second, this is almost u prime times u to the negative 2. You see what I'm talking about?
Yeah.
I just need to put what there?
3. Just a 3.
Negative
I
3.
need
Just a
positive 3,
3,
right?
Yeah.
Because the derivative, if this is u,
Oh, sorry, I was thinking of integral.
it's okay. So the derivative of sine of 3x, this is my u, this guy's u, the whole thing, is 3 cosine of 3x. So I gotta put a 1/3 out here to balance it. And so then you perceive this will of course turn into negative u to the negative first, right? And then for b, who is u there?
That one is.
It's, yeah.
Wait, hold on. I already did this problem, but it's
Yeah.
in my bag and I don't want to.
So this dude is the u.
I don't want to get it out.
Right, Aaron?
Yep.
Yeah.
And then, so this guy's almost u prime. So I gotta put a 2 and a 1/2. And then what you gotta do is go, I don't, maybe you don't have memorized what's the antiderivative of tangent, but we know that we've done that question before, right?
Yeah.
So we talked about, was it yesterday or the day
So
before?
tangent, yeah.
The integral of tangent is gonna be negative log of cosine. So
Yes.
Right?
Yeah.
Okay.
Jay
Bye,
Hall.
everyone.
Natural log and cosine?
Yes.
Well, that's one, make sure you understand that one. Make sure you know what the antiderivative of tangent is. Yeah, negative log of cosine, sounds right.
Sounds right.